now you've seen the magic of piping, you've seen the magic of, well, different tools. Now we're going to see how we can handle some tabular data, tables here, trying not to get overwhelmed by the number of columns, by the number of, the amount of information that we can find in a file. So do you remember we have this file called sequence.gff3, right? So one of the first things that we want to do is we want to find out how many lines it actually has. We want to know how many records are stored in this file, because that's going to tell us more or less how big the file is, what kind of records we're going to have. So for that, we're going to use the command word count again. Remember that we just used word count, WC, yeah, to count the number of characters in a line. Yeah, now we're going to use the command word count, WC, to count the number of lines in a file. Yeah, now, if you want to know how to do it, you can always go man word count, and it's going to tell you. If you want to count bytes, you use -c. If you want to use characters, -m. There is a difference between bytes and characters, but I'm not going to go in there. If you want to count the number of lines, -l. If you want to use the number of words, -w. And there are a lot of other options. I don't know how to use them all, so don't ask me. Sometimes Google knows. So you've seen that in order to count the number of lines, we have to use the flag -l. So what we're going to do is word count -l. Are we okay so far? We all got to run this? Now, we're going to we want to get a feeling of what it looks like. We've already seen it in Vim, right? We just saw Vim, and we moved around, we took a look. It looks a bit challenging. So let's just do ahead. We're just trying to explore this thing, trying to know how to handle it. We've already seen that this table is separated by tabs. Yeah, that's something we already know. Yeah, so it would be useful if we didn't show all the columns at the same time. Do you think it would be useful if we just showed a few of the columns so that it doesn't look so crowded? So that's where we start using the keyword, the command cut. C-U-T, cut. Cut is going to perform an operation on the file, yeah, that it's going to just select which columns we want to display. For example, if we say column -f1 and sequence.gff3, who wants to guess what's going to happen? There are no wrong answers. Yeah, it is just a wild guess. Probably you have never used cut, so you don't know what it does. But if I tell, this is going to handle my columns, yeah, and I told you a cut -f1, what do you think is going to happen? What column are we going to show? Are we going to display? That's perfect. The first line, the first column. So let's see if it holds true. Only the first column. Of course, this is still way too much. Let's pipe it. I want to see the first column, but only the first 10 lines. Because I just want to have a feeling of what it looks like. All right? So yeah, that's it. That's what we have in the first column, in the first 10 lines, and the first 10 columns. On the first column, sorry. That's all we've got. Now let's take a look at because one column is not enough, right? Let's take a look at the first 5 columns. How do we do that? Instead of saying just cut -f1, cut -f1 to 5, 1-5. That's going to show me columns 1, 2, 3, 4, 5 of the entire table, and then I pipe it, and I say just show me the head. Just show me the first 10. Does this make sense so far? Do you have any questions regarding this? So the command cut will tell me cut the table and show me only these columns from 1 to 5. And then, instead of showing the whole table, I'm piping it into a head command. And the head command is going to show me only the first 10 lines. So what we're going to see right now is the first 5 columns of the first 10 lines. That's it. Just to get a feeling of what the data looks like. Well, it looks a lot better than just looking at the complete cram table, doesn't it? It looks cleaner. It helps you look for important data, like what columns are important to you. So you can see, for example, right now that one of the informative columns here is going to be the third one. Here it says region, sequence feature. You have gene, we have tRNAs, we have exon, gene, CDS, gene. So we know already that we have an important column there because it is informative. It's telling me that we have different notations, and these different notations have different classifications. Some of them are genes, some of them are tRNAs, some of them are exons, some of them are genes, some of them are CDS, coding sequences. There's a big nomenclature of what these things are. Yeah, if we add more columns, we'll see that there is more information, but let's not overlap them. Let's just save whatever is useful. For example, we want to see column 1, we want to see column 3, we want to see column 3 to column 5 to column 7. We can also do this. I just wanted to show me column 1, and then from column 3 to column 7. Does that make sense? 1, 3 to 7. So let's take a look at it. There we go. We also have another informative column. The last one, it has plus, plus, minus, 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 minus. That is actually telling you in what strand the annotation is happening. So if we wanted to know, for example, and this is just a crazy idea, is let's say we want to know how many features are annotated on the plus strand, on the forward strand. That's all we want to know, right? So what we get is we're going to try to capture only the columns that have a plus sign on this column number 7. Yeah, this is going to be this is going to look a bit awkward, yeah, because this is using another command tool. It is actually a programming language. It's called awk, yeah, but it's pretty straightforward. Basically, we said awk, yeah, and we say column 7 equal plus. We're saying we only want to display all the lines that have a plus in the column 7, because we already know that's the one we want. Where? In sequence.gff3. Now, you're going to see a display of everything that has a plus. So it's going to look ugly, right? Let's just cut it to minus F1 to 7. Just to make it look prettier, just the first 7 columns. It looks better, and you can see that we're only capturing those that have a plus. Now, what we wanted to know is how many of them, of these columns are there. So, what we do is instead of piping it to a cut, we pipe it to a word count, just like we did before. We want to know how many lines in this file have a plus sign on the column 7. 169. And do any of you remember how many lines were in total? Now, you have to remember that the first 3 or 4 lines are comments. Yeah, they don't have any actual annotation. It's just a general description of what the file contains. Yeah, but if we do the opposite, if we do count how many have a minus, now awk is a little more advanced Linux scripting, but it's also very useful. Yeah, we probably will be touching that on the assembly practice. Yeah, but suffice to know right now that you can filter all these by columns. You can do the filtering based with awk. Now let's say that we want to sort it, and now sort is also a very powerful tool. Let's sort it alphabetically by the name of the feature. That is, by these names, exon, CDS, genes, etc. Let's sort it by that. Let's put all the genes together in a single block. Let's put all the exons together in a single block. Let's put all the CDSs together in a single block. How do we do that? We use the command sort. Now, to use the command sort, we have to tell it what column to sort by. So in this case, we want to see the CDSs, the exons, the genes all crammed together. What column is that? This is column number 3. Look, 1, 2, 3. So what we do is minus K is going to let me know, it's going to tell me, tell the number of the column from column 3 to column 3 of sequence.gff. Since I don't want to see the whole file, let's just see the head, okay? It looks ugly, but you can see that all the CDSs are crammed together. You'll see that when you do the head of the sequence.gff, the original GFF, yeah, you'll see that you have region, sequence, gene, tRNA, exon, gene, CDS, gene. After the sort command, which we saw above, which is this one here, you'll see that all the CDS features are crammed together. We've sorted it alphabetically in the based on column number 3. Now let's say we want to find out how many CDS. Anybody wants to get a guess? Just take this example. If you take a look at your notes, just remember how we use awk and change it. Just change the command of awk so you can tell me how to select only the columns that have. I'm going to write here what's the command of awk that we used before. That's the command we used before. What would you change in that command to select only those that have genes, the code word exon on column 3? The plus, what would you change the plus for? Exon, very good. And what else? There's only one. That's it, as simple as that. Is in awk, instead of putting column 7, you put column 3. And then you say it has to be equal to. Yeah, so basically what we're going to do is we're going to select only the exon features in column 3. And we're going to show just the first 10 hits. Yeah, and we're going to show only the first 7 columns. You see there's an error. I don't know how to write, how to type. There we go. All of the results are exon. Those are the first 10 exons that we found in this file. Now, if we wanted to know how many exons there are, we just replace the head and cut with a simple word, WC minus L. It will tell me there are 81 exons. Now, let's say we want a summary of this. Yeah, we want a full-on summary of how many exons, how many CDSs, how many of these features we actually find. Yeah, because I'm not going to run them, each one of them individually. I want to know how many there are and which there are. That's where we start using the unique command. This is the command, unique. Basically, unique is going to merge in a single line all the lines that are exactly the same. So we're going to have to process a little bit the table because there are no 2 lines that are exactly the same. There are going to be some lines that have exon and exon, but the rest of the record is going to be completely different because these are different coordinates, different genes, different exon entries. Yeah, but we are only interested in that column 3. So the first thing is we're going to extract the column 3 from the table. Who wants to tell me how do we extract? We only want to display column 3 from the table. Go ahead. Don't worry. There is no wrong answer. Yes. Perfect. Perfect. That's it. Cut minus F3. So we first use cut minus F3. Sequence.gff3. Yep. Is that the list we wanted? That looks like it, right? That looks like the list of just the column 3. That's the only one we wanted. Now there are lines that are identical to each other. For example, CDS here is the same as CDS here. So now what we need to do is sort them in such a way that similar words are crammed together. Yeah, one after the other. What do we use to sort? I just said the name. In order to sort, we use the command sort. Perfect. So what we do, we pipe it. We pipe it to sort. Since there is only one column, we don't need to specify from which column to which column. We just do a sort. Let's enter, and you will see that you already have it sorted. And now, what we're going to do is we're going to include the word unique. This command unique has many different flavors, many different options. We're going to use the option -C, which means count. I want to count how many of each of these identical lines appear in this table. So let's just count them. This is going to tell me, without any bias, how many of these code words in column 3 we have on the table. For example, the table has one space. That is an empty line. The table has 103 CDSs, 81 exons, 140 genes, 4 origin of replications, 3 pseudogenes, 1 region, 8 ribosomal RNA, 9 sequence feature, and well, these are comments, so just don't mind these ones. It has 4 STS, and then it has 45 transfer RNA. That is all the genes that have been encoded or have been annotated in the potato chloroplast genome. That's it. You have a list of all the things that have been annotated there. You don't have, in this table, in this summary, we don't have the start or the end locations. We don't have the orientations, but we do have a summary, an overall summary. We didn't have to go through all the file manually and look and start counting and keep separate counts of each. No, we can do it all this by using simple Linux command. Now, if you wanted to do this on Windows, yeah, you'll take forever. If you want to use a bigger table, it's going to take even longer. Yeah, this is a very small genome. This is just a 155K kilobases genome. Imagine if you have to deal with something like potato genome, the Arabidopsis genome. If you have to use, there is this tree which has 20 gigabases, the lovely pine genome, 20 gigabases, 20 billion base pairs, and you have genes and pseudogenes and transference RNA and all these kind of features encoded there. How do you get a summary of all that? Of course, right now you're going to say, hey, how can I run this over and over and over? It would be very useful if we can run this over and over and maybe even save some intermediate files. So you've seen the power of piping. Now we'll see the power of scripting. We're going to create our first program, our first script in Bash. And as I mentioned before, what is a script? A script is simply a sequence of commands that will give you that will take you from one starting point to a final outcome. Yeah, it's going to just be a series of commands. And for that, we're going to create an empty file, an empty bash script. How? We use Vim. Vim is our text editor. And let's just be creative, and each of you is going to create your own name. For example, I'm going to create this. You can put the .sh or you can skip it. It's not important. But I'm just putting it like Inia first program. Look how I've avoided using spaces. I've replaced spaces with underscores. This is recommended practice in Linux. Okay, so now we've got our first program and it's empty. Let's create it. The first thing we're going to do, let's say we want to create a new directory. Does that sound feasible? Have we created directories before? Yeah. Who can tell me the command for making a mkdir? So let's just do that as the first step. Oh, by the way, in order to start writing, you have to press the button I. All right? So mkdir, and be creative. Just create whatever. Now what can we do with test one? Let's just put some results there. Do you remember the pipe we just did, where we generated this summary table? Basically what we did is we cut minus F3 of sequence.gff3. Then what we did was sort it. Then we did unique minus C in order to get counts of each of the features that we set. And okay, let's leave it there. You're not writing? Oh, you have to push I. Press the key I. Yeah. Also, you have the key insert. Yeah. If you push that, you should be able to start writing under Vim. So there are only 3 lines here. The first line is mkdir test1. What is it doing? Who can tell me what that line does? mkdir test1, creating a folder. Very good. It's creating a folder wherever I'm placed. Just keep that in mind. That is, wherever I run this, yeah, it's going to create a test1 folder in that location. Okay? What is the second line doing? Oh, yeah. Cool. So what is this cut minus F3, sequence GFF3, pipe into sort and unique? What is that doing? So do you remember? Yeah, exactly. That's it. This is something I forgot to tell you. This is the redirection. This just greater than sign. This is actually telling me that the output of the pipe that I just created, the pipe that we just saw, I'm not going to write it, I'm not going to display it. I want to save it into a file. And what file is that going to be? It's going to be in the directory that I just created, test1, and it's going to be called test1.txt. This is what this is telling me. So once this all is finished running, it's going to save the table, the summary table we got, and save it into test1/test1.txt. And finally, just to make sure that the program finished correctly, yeah, we're going to run this echo. Echo is just a way to say to the bash script, hey, display this in the screen for me. So once this command is finished running, the bash script is going to tell you your first script has finished. Now, in order to save this script, let's press the button ESC so that you cannot write anything anymore. Then write period, and then WQ. This is save and exit. Save the current file, WQ, and enter. Now, before you do anything else, please list the content of your folder, of your directory. You can see that you have 4 files, right? You have all the sequence FASTA files, the sequence GFF3 file, sequence 2 FASTA file, and also Inia first program.sh. Now, if you want to see what's inside the Inia program, yeah, you just use cat. Cat, C-A-T, Inia first program, and you'll see that you have only these 3 lines. Now, we're gonna test if this runs or not. How do we test this? We're gonna run it using the keyword bash. Bash Inia first program.sh. It is as simple as that. I'm gonna press enter, and you'll see that the only line that appears is first script has finished. Can you please all run this command? First, check that the file has been saved correctly by listing the directory. Then, show that the program contains the 3 lines that we just wrote into it. And third, execute the command, the program, this little script, in order to see that last line flash there. Can you show me? How did it go? First script has finished. Yeah, so press ESC, list of your directory. Just follow the commands I did there. Please feel free to interrupt me if I'm going way too fast. I know this is a lot to learn in one single day, and I don't want to overwhelm you with a lot of information. So if I'm going too fast, please just feel free to stop me. Yes? All right, so where did you get to see how we were getting all this summary data and that stuff? All right. Doesn't matter. We'll fix that out in a bit. Sorry. How are you guys? You were also absent? Yeah. No, that's okay. That's okay. What comes first? How's it going? All right. How are you doing? All good? Did it run? Okay. All right. Cool. Yep. Bash. And this is all that needed to appear. First, the script has finished. Now, after this is finished, now list. Do the LL. Run LL. Look, you have created this. Can you go in there to the test one? So is everybody already there? Have you guys successfully run your first program? Or anybody's having any issues? Bash es el lenguaje What is bash, if you're asking me? Bash is just the default scripting language for the shell in Linux. That's the user interface. It's like the basic line of commands to handle most things in Linux. Managing files, accessing directory, etc. It's done in bash. It's like a scripting language. It's a programming language. Once it's created, it won't overwrite it. Yeah. How did it go? All good? Great. Now, have you guys all been able to see that the final file, the test1.txt, is written where we were expecting it to be written, and that it contains what we were expecting it to contain? Have you guys checked that? I know we're in a hurry, but this is always important to do. Make sure that your programs do what you were expecting them to do. So what were we expecting this program to do? To generate a summary table, and that this summary table appears under a directory called test1. So the first step was creating test1. Check. Test1 has been created. So let's log in there. And then we do have a new file written here. It's called test1.txt. Was that the name of the file that we said we wanted? Yes. If you see, when we redirected, it said we want to create a file called test1.txt under the directory we just created, test1. Yeah? And what should this contain? This should contain a summary, the same summary we just got before. So that's a summary. That's a summary of all the features that were annotated in this GFF3 file. We've saved it. We already have the summary written somewhere in this file. We should know where it is. So yeah, this is your first bash script for some of you. For other people, probably you've already written better bash scripts, but this is a first step. You can just start increasing it, decreasing it, changing, using new commands, and just improving your overall scripting. I think that's it for today. Thank you very much for your attention. If you have any further questions, please feel free to ask them right now, later, tomorrow, whenever you want. Yes? Yes, you can save it. Don't worry about this. When you exit, this is gonna be saved like a session. So you'll go to machine and just log out or close. Save this machine state. Yes. It's going to save the changes so that next time you open it, it's going to have the same things that you have already set up here. And that's it. Thank you very much for your attention.